video, we will study about projectile motion, topic 12.6. What is a projectile motion? So let's look at this example. A player kicks off the ball with some initial velocity and angle, and once the ball is being kicked, the ball travels freely in the air and it lands at point B. Now the motion of the ball from A to B after it has been kicked off is called free flight motion, because during this motion the ball is purely traveling with the initial given velocity and under the influence of gravity. And we know that the gravitational acceleration always wants to pull things down towards the center of the earth. So that's why the ball with some initial velocity travels up to some point at certain maximum height, and then the gravity brings it down all the way up to point B. So any application where a particle, now it can be a ball or it can be a glider or any other example that has like free flight purely under the influence of gravity, we can analyze that motion using projectile equations. For now, we limit ourselves to only two-dimension projectile motion, where we define the x-axis as going right and y-axis positive going up. And since gravity is always downward, we consider the gravitational acceleration as negative. Also, observe that the gravity only affects along the vertical direction. There is no acceleration along horizontal direction. Having said that in mind, so let's look at the few application examples of projectile. So, objective is to analyze the free flight motion of a projectile. So these are all the different applications of projectile, where gravel falling off the conveyor is type of a projectile motion, because once the gravel leaves the conveyor with some velocity at some angle, it's free flight and it's landing at certain distance. So depending on how far and how high we want the gravel to land, we can calculate the required velocity of the conveyor or required angle of the conveyor. Same here, the sex slides off the ramp, that's also a projectile motion. Chipping machine, which throws wood chip at certain distance. So depending on the angle and velocity of the wood chips coming out from the machine, we can calculate how far and how high will that land. Rider jumps off the slope, that's a projectile motion. For example, high jump using like motorcycles or monster truck or cars. Football or any game that involves ball, for example, golf or baseball or cricket, where a ball is being hit with some initial velocity and then its motion is free flight, and we can apply projectile equations to simplify the motion. For example, a ball launcher here launches the ball with some velocity and angle so that the ball can strike at point B at certain height. Skier jumps off the ramp. So this ramp has been designed such that skier jumps off the ramp at some velocity, some angle. Now, it's very important to consider that projectile calculation here, because we would like to make sure that the skier lands safely at point B. And for that, depending on the distance where we want the skier to land, we can actually back calculate and design the ramp for skier jump. In this example, a missile goes from A to B, and then it changes the angle, and then all of a sudden engine stops working. So it has the initial momentum, it has that initial velocity and angle. So without engines running, how far this rocket or missile will land, and that can be done using projectile. Firefighter, projectile application. Water fountain, projectile application. In the purpose of the water fountain is to make sure that the water lands within certain area like B and C. So depending on that area, the flow rate of the water can be calculated so that at certain minimum or maximum velocity, water always lands between B, C and not outside the water fountain area. Even more sophisticated and advanced application is NASA's mission to the moon. So in 1969, when NASA launched Apollo 11 to the moon, that was a huge projectile motion that actually they threw the rocket towards the moon. So would there be no moon, the rocket would have gone all the way up to certain height and came back to the earth via projectile motion like this. But because there was moon, the gravity of the moon influenced the rocket and it pulled the rocket and it landed on the surface of the moon. So this journey of 954 mile total distance traveled by the rocket, the actual engine of the rocket was running only for some fraction of time. For most of the other time, the rocket was just traveling under the influence of gravity. So these are different applications of projectile motion. And now we will look at the equations, how this projectile motion is being calculated, or how can we calculate the position or velocity of objects in the projectile motion. So we have seen these equations in the first class or the first lecture, how velocity, acceleration, and position are related to each other. So velocity is given as a function of time, and if the acceleration is constant, then we can pre-integrate those equations and derive this formula for final position velocity using the velocity and acceleration equation. So using this formula was actually applied to rectilinear motion, that is motion of the particle only along one direction or x direction, x-axis only. Now we can apply this concept to projectile motion, which is two-dimension motion. So as we can see here that the particle is launched with, for example, this ball is launched with some initial velocity and angle from point A, and then it's traveling under the free flight and landing at some distance from the point of launch. And for that, we need to apply these equations. Now, let's define our coordinate system that horizontal motion is going right, positive, and that's our x coordinate. Y coordinate is going up, that is positive. Now, there is no acceleration along x direction, so x acceleration is 0, and acceleration along y direction at all the point is gravity, which is minus g, which is minus 9.81 meter per second square if it is SI system, or 32.2 feet per second square if it is FPS system. So what basically we would like to do next is we will write each one of these equation separately for x and y coordinate. So we break down the motion of the particle along x and y, and for each motion we will write the equation using projectile. So let's look at this. So this is how each equation is written for, let's say first we write the equation for x-axis. So we use, instead of s, now we use variable x. So v equal to v0 plus act, x equal to x0 plus v0t plus 1/2 act square, v square equal to v0 square plus 2ac x minus x0. Basically what we have done is we replace s by variable x because we are writing this equation only for x-axis, which is positive motion going right. Now there is no acceleration along x-axis, that means this component is 0. That means vx, or velocity at any point x, is same as the initial velocity. Same way we get the second equation and third equation by substituting the value of acceleration. So x acceleration is 0, so x is x0 plus v0 xt. Now it's really important to pay observation to these two equations, because what they say that the velocity at any point is same as the initial velocity for x-axis. That means no change in x coordinate or x velocity vx of the particle. Now if we apply that to only y motion, which is vertical going up, then we have three equations here, and then we substitute acceleration equal to negative of gravity because gravity acts down, and we define that the positive motion is going up. Then this can be calculated as velocity in y direction is this, velocity position in y direction can be defined using this equation, and there is also third equation. So now because the first two equations are same here, we can consider this as equation number 1, equation number 2, equation number 3, equation number 4, and equation number 5. So we have 5 equations for projectile motion, 2 more equations for x component of the projectile motion, and 3 equations for y component of the projectile motion. And now we will solve the problems involving projectile calculation. That means if we know the initial velocity and angle of the projectile launch, using those equations we can calculate how high that object will go in the air and how far, we call this x max, that object will travel along the horizontal direction. So we can calculate these two parameters using those equations. We can also do the reverse calculation such that if we know that we want the projectile to go at certain height, at certain distance, then we can back calculate what should be the velocity and angle of the projectile. Okay, so let's look at one example of that type in the application. So if we look at this application, let's say this person wants to throw a ball and send it to the basket. Now every time if he wants to do that, he is doing that from a fixed position, he can do that precisely if he knows how far is the basket from where he is standing, which is called x max, and how high is along y axis. So once he knows those two parameters, he can actually back calculate what should be the initial velocity and the angle of the ball launch so that ball will always like go to the basket.